They noticed kind of similar correlation, positive correlation with the volcanic output rates for different arc segments, where the volcanism rates, they increase with increasing thermal parameter. So those two things seem to vary, and they seem to be correlated with this thermal parameter. But you can, there's another feature, geodynamic feature of subduction zones that is usually symbolized by D, and it's sort of a geometric feature. It is the depth to volcanic arcs beneath, or the depth to oceanic slabs beneath volcanic arcs. So if you have an arc here and you drop a plumb line straight down to the slab, the depth between the arc and the slab in a vertical sense is symbolized by this D value. And what Watt and Wong have noticed, same as others have noticed, including England et al. In 2004, is that while the D value ranges quite substantially from segment to segment, it doesn't seem to be correlated at all with the thermal parameter. So this is shown on the bottom plot. Here's a purple band of the ranges of these D values. All of the data points represent these D values, which you can estimate from the hypocenters of earthquakes. And they kind of vary all over the place, but they don't seem to be positively correlated or negatively correlated at all with thermal parameter. So how do we explain this? How do we explain that some geodynamic features of subduction zones seem to vary and they're correlated with thermal parameter, and this one particular geodynamic feature is not correlated with thermal parameter? Well, Watt and Wong set up some numerical simulations of subduction, and they implement a coupling depth, which basically controls the point along the slab mantle interface where the oceanic plate and the upper plate viscously couple and start to drive mantle wedge circulation. And they took a look at the empirical heat flow data, and what they did was they adjusted the coupling depth in the numerical simulations up and down to the point where the calculated surface heat flow matched or fit the empirical data. And what they found, surprisingly, was that for all of these different subduction zones with varying thermal parameters, a coupling depth at around 75 kilometers seemed to fit the empirical data quite well, irrespective of the segment. So the notion is that the depth of coupling between plates might be invariant among subduction zones or narrowly distributed. And therefore the D value, which must be associated in some way, shape, or form with the coupling depth, it must also be invariant. However, this whole notion that there is a feature of subduction zones that is uniform or invariant from segment to segment, I think comes out of perhaps a poorly worded question. So while Watt and Wong in 2009 asked, why is D uniform with respect to phi? The question itself sort of implies an invariance of D with respect to any subduction parameter at all. To make this more clear, if you go back to the study of England and all in 2004, already they demonstrate that there is a huge variation in D. D varies from something like 65 kilometers to 130 kilometers. You can see on the top two plots, here is from the England and all 2004 paper. This is the D value with respect to the oceanic plate age on the top left, the D value with respect to the thermal parameter on the top right. And while these D values aren't correlated with age or thermal parameter, they are not uniform, okay? In the strict sense of the word, they are not the same. They do vary from subduction zone to subduction zone quite a lot. So I think the question, the wording of the question, why is D uniform, kind of led to this notion that subduction zones, there seems to be some features that are invariant, where this doesn't seem to be the case. But regardless, however imperfect the wording of the question, the results of the study of Wada and Wang in 2009 do lead to this really key insight, and that is that the variations in D that are there, that are measured, are perhaps and probably related to variations in coupling depths. And so this leads to maybe a better question. We can ask ourselves, well, how uniform are coupling depths? How do they vary from subduction zone to subduction zone? So in part one, we're going to evaluate the distribution of coupling depths using numerical simulations. These are the research questions that we attempt to answer. First, what controls the depths of mechanical coupling? Is it metamorphic dehydration reactions in the slab? Does it have something to do with dehydration reactions in the mantle wedge? Second, is coupling depth invariant with time? In other words, do coupling depths stabilize after initiation? And if they do, how quickly? And lastly, is coupling depth invariant with subduction zone setting? So getting to the same question is like, how much does coupling vary among subduction zones, and does it or does it not correlate with the thermal parameter? So we set up a suite of 64 numerical simulations of oceanic continental convergence. The figure on the right is an example of one of these particular simulations, 1 out of 64, where we observe the coupling depth by visualizing the viscosity and the temperature fields, and you can sort of pinpoint the depth of coupling by carefully looking at things like the strain rate, the viscosity, and the temperature. And what we notice is that in these particular simulations that we set up, the coupling depth always is associated with the dehydration of serpentine in the mantle wedge. This is kind of like what controls the coupling depth in our model. And in the diagram, in the figure here, I'm not sure if you can see my cursor. Oh, you can, great. So there's like a very thin pink layer in the mantle wedge. I made this layer pink. It represents the markers here that are serpentine. They're antigrite markers. And I made them pink to kind of emphasize where this layer is, because wherever you have this thin layer of antigrite, the plates are allowed to kind of move past each other. And wherever the antigrite dehydrates, it's no longer stable because the temperatures are too high. That's the point at which the slab and the mantle begin to couple. So in the models themselves, the parameters that are fixed or controlled for are the Ray logic model. We use temperature, pressure dependent viscoplastic deformation in the whole model domain. The hydrologic model is fixed. It involves the expulsion of pore fluids and connate water and sediments in oceanic crust, and then sort of a continuous dehydration relating to eclogitization of the oceanic crust. And also we implement this antigrite dehydration hydration reaction in the mantle. And the material properties are all empirically derived. Those are constant for all the simulations, and the boundary conditions are also constant. There's a free surface, there's an open bottom boundary, so the slab motion itself is spontaneous. And we impose a kind of a constant horizontal convergence force near the edges of the boundaries. And the parameters that we vary are the velocity, the oceanic plate age, and those two things, if you take their product, you get the thermal parameter. So this is kind of what we're trying to evaluate any correlations with respect to. But also in 2004 in England et al.'s paper, they also sort of allude or they predict that the thickness of the upper plate is another important parameter that might control this D value, the distribution of this D value. So we went ahead and tested that too. Here are the results. So for all 64 numerical simulations, we find on the left, there's a very, very strong correlation with between the upper plate thickness and the coupling depth. So that's the figure on the left. It's quasi-linear. It's a little bit better fit with a quadratic curve, but nonetheless, there's a strong positive correlation between the thickness of the upper plate and the coupling depth. And with respect to the thermal parameter, we find exactly what England et al. In 2014 and 2010, and what Syracuse and others have found in previous work is that irrespective of the thermal parameter, the coupling depths, they range all over the place, just like D values, and they're not correlated really at all with respect to the thermal parameter. I see a hand up. You want to ask a question? Go ahead.
Can you clarify what is the upper plate thickness in what's your definition of this?
Sure, thanks. The definition is the temperature. We use the 1100 degrees C isotherm for the thickness of the upper plate. So we define this, well, we first define this using that temperature, and then in the models, we adjust the heat flow so that we get that thickness, the correct thickness in the model. So it's a thermal definition of the base of the lithosphere. We use the 1100 degrees C isotherm in this case, and this corresponds to when we visualize the models. If you look at the viscosity contrast, it also corresponds really well with the difference in viscosity between the lithosphere and the asthenosphere. Thanks for the question. Okay, so we have all these numerical results. So we ran 64 simulations. We know the thickness of the upper plate lithosphere in the simulations. We know the thermal parameter. We've observed or measured or determined the coupling depth in all of the simulations. And so what we can do is we can regress some expressions that relate the coupling depth as a function of upper plate thickness and the thermal parameter. So we use three different expressions. One is linear, that's the top left plot. One is, the other two are quadratic of two slightly different flavors. That's the top right plot and the bottom left plot. And the points that you see on the plots, the top left plot, the black squares are the numerical simulations that we use to regress these contours. So the contours themselves represent the coupling depth. The x-axis is thermal parameter. The y-axis is upper plate thickness. And the black squares are the numerical simulations we use to regress the contours. And the white data points are empirical data. So there's some information for modern day subduction zones where we use the average heat flow to calculate the thickness of the upper plate for those subduction zone segments. We know the velocity, the ages of the slabs, and so we can plot them on these regressed expressions, and thus we can calculate the predicted coupling depth for these particular subduction zones. And what we find is that in the bottom right plot shows the distribution of the predicted coupling depths for these 13 subduction zones. And we find that they center around 80 kilometers depth, and they have a pretty narrow-ish distribution of about plus or minus 20 kilometers. This is very consistent with what Wad and Wong have found. And the key insight here is that these expressions that we regress suggest that the coupling depth is really, it can almost be exactly approximated by just using the thickness of the upper plate. In other words, the response of coupling depth to the thickness of the upper plate is so strong that the upper plate thickness can almost give you exactly the coupling depth with just a small correction. Okay, so they're almost equivalent. They approximate each other. And so the expression kind of leads us into the following question, is how thick are upper plates globally? So in order for this notion that the D value and coupling is invariant, we see from this expression that would suggest that the thicknesses of upper plates must be invariant. If the notion is true, then the thicknesses of the upper plates must be also similar and sort of uniform from setting to setting. And this leads us to sort of a testable hypothesis, because we have empirical data for surface heat flow. So for part 2, what we can do is we can sort of investigate the average thicknesses and the sort of variation in upper plate thicknesses by looking at empirical data now, namely surface heat flow. So it looks sort of like this. So it's been well known for a long time. There's been a lot of studies that have derived models to sort of invert the thickness of the lithosphere from surface heat flow. And we use a similar approach, and the approach looks sort of like this. It can be diagrammed or illustrated using the plot on the left. So the plot on the left is some heat flow data that's calculated from our numerical experiments. And you can see that the heat flow of the incoming slab, they're all the same slab, so the heat flow is all the same. It dips down a little bit as it goes into the trench. And then behind the arc, the heat flow starts to kind of diverge. And the divergence, or the separation of all those heat flow, is a function of the thickness of the upper plate lithosphere. So for very, very thin lithospheres, which would be like the yellow line, it's got a very thin 46 kilometer thick lithosphere, is probably absurdly thin, has high heat flow. And the heat flow decreases as the thickness of the lithosphere increases. So in theory, in principle, we can go and look at surface heat flow, and we can use some pretty simple one-dimensional steady state heat conduction formulations to calculate the thickness of lithospheres. So here's our questions. How thick are upper plates? First of all, are they uniform, or do they vary among subduction zone settings? What is the two-dimensional variability? So how do these things change along strike? Are they uniform, or are they variable perpendicular to the trench, along strike? And how precisely can the thickness be inferred? What data sets can be used, and what are the uncertainties, of course? So the data set that we turn to is the most modern, most recent, and most well-maintained global database for surface heat flow. It's called ThermoGlobe. It's maintained at by Jennings and Derek Hastrock. I believe they're at the University of Adelaide in Australia. I could be wrong. They're at one of the Australian universities. There's approximately 70,000 data points in this global heat flow database, and they are variable quality. A lot of these data points are proprietary. They come from all different sources. They span decades and decades. And so the sort of quality control and quality assurance of the database itself is an ongoing endeavor. Okay, but nevertheless, we take these data, we filter them for quality the best that we can. We clean them up. We crop them to within 1,000 kilometers of 13 subduction zone segments, which you can see here on the map. And we apply two different interpolation techniques to distribute these individual discrete measurements into a two-dimensional view, two-dimensional approximation of the continuous surface heat flow. The interpolation methods that we use are fundamentally based on two different laws of geography. So we use a method called similarity, which states that similar geographic configurations should have similar values of the same process under investigation. So what does that mean? In other words, if we have, if we know that, for example, we're on a craton and that the rocks are very, very old and the rocks are the crust is very, very thick and it's not very radiogenic, and we measure the heat flow there, we'll find that it has some particular heat flow value. Now, if I go to another craton and I know it's a craton, I know the crust is very thick, I assume or estimate that it's very unradiogenic, then because of the similarity of those two different locations, irrespective of where they are around the world, I predict that those two locations should have similar heat flow. Same example goes for mid-ocean ridge. If I know I'm within a few kilometers of the spreading center, I'm going to measure high heat flow. If I go to any other spreading center, irrespective of where that spreading center is, I will predict that I will measure a similarly high heat flow value. Okay, so similarity brings in our geologic knowledge to sort of estimate heat flow, and it's completely ignorant of the spatial information, which is the opposite of the other technique that we use, which is called kriging, which a lot of people are familiar with. The fundamental law states that everything is related, but nearer things are more related. So kriging doesn't consider any geologic information at all. All it considers is, I measured heat flow here. If I move 5 meters away and take another heat flow measurement, I would predict that those two heat flow measurements should be very similar. If I measure heat flow here and I go maybe 15 kilometers away, I would expect that those two heat flow measurements are unlikely to be correlated with each other. Okay, so kriging is a method that only considers the spatial continuity of measurements or observations. Similarity is totally ignorant of that and just uses raw geologic information to make predictions. So the plot on the right shows Central America, and at the top is the thermoglobe database. You can see all the discrete measurements. The locations of the measurements are associated with certain geologic features, usually because those things are interesting. So there's a lot of measurements near mid-ocean ridges and in areas with active volcanism and in other places. And then you can see that there's whole regions, especially in the back arc, where heat flow observations are incredibly sparse. So the challenge is to take all these sparse and discrete measurements and do some approximation of the two-dimensional continuous heat flow. The plot on the bottom shows the similarity interpolation. So you can see that near the mid-ocean ridges, similarity says, okay, I know I'm near a spreading center, I'm predicting high heat flow, and there's some kind of discrete regions where there's high heat flow. These are probably related to locations of volcanic vents and other things. And for the most part, the picture looks pretty reasonable. For kriging, there is a procedure that is very sensitive to a bunch of kriging parameters. So the kriging parameters include something called a variogram model that you have to fit to observations. There's 5 parameters that go into making this calculation, which are shown at the very bottom on the left here. Don't really have to understand what these are, but you should understand that kriging is very sensitive to all of these different things. And it is commonplace in the world of doing kriging calculations to adjust these parameters ad hoc by eye, fitting variograms, these so-called variograms, to data points. You're basically fitting a line through some data points, and geographers and other folks who do this sort of quantitative work will often just fit a line that looks best, visually looks best. Now, because we're investigating all of these different subduction zones, the variability in the distribution of heat flow, is so great that it's really, really challenging to, and it would be very time consuming to do this over and over and over again, to kind of manually adjust the Kriging parameters for each one of these things. So what we devised is an algorithm, an optimization algorithm that tries to minimize two different things. It tries to minimize the misfit of the variogram model to the data points, but it simultaneously tries to minimize the misfit or the error between the actual heat flow observations and the predicted values. So it goes through this iterative process where it predicts some heat flow. It looks at how well that heat flow compares to the actual measurements, and then it goes back and adjusts the parameters, and it tries to find some global minimum using this iterative algorithmic approach. So what we find between the Kriging predictions and the similarity predictions are very subtle differences. For the most part, the predictions, the interpolations, their accuracies are broadly comparable. The distributions of the heat flow predictions are broadly comparable, but there are subtle differences. So this is an example of the Vanuatu subduction zone. And I'll just draw your attention to the microplate to the very, very north. So the black lines are the plate boundaries. The white line is the basically location of the trench. The gold diamonds are locations of volcanic vents. And then the color represents the heat flow. Cool colors, low heat flow, warm colors, high heat flow. And if you look at this northernmost microplate here, the similarity is, similarity is predicting that there's a rather high heat flow within that northernmost microplate, whereas Kriging is predicting that the heat flow in that microplate is quite low. There seems to be some discrepancy between the Kriging prediction and the similarity prediction in this case. Why is there a discrepancy? Well, it's because the actual heat flow measurements in that microplate are low. Kriging is seeing low heat flow measurements, and it is forced to predict low heat flow for that particular region. Whereas similarity just sees that there are plate boundaries there and volcanic vents. And so it's predicting high heat flow, and it's completely ignoring what the observations are telling it. So we have two different methods that are, because they have fundamentally different mathematical models behind them, there are these subtle little differences that pop up in the predictions. And the useful thing is that these subtle differences can be pointing to features that are interesting. They're interesting for many different reasons, and they could be sort of targeted for future heat flow surveys. Now, going to the distribution of surface heat flow in the upper plates, which our goal is to understand how the heat flow is distributed along strike and perpendicular to the trench in the upper plate, so that we can get some sense of the thickness of the upper plate, so we can get some sense of the distribution of coupling depths. Okay, so when we look at the distribution now, we take the heat flow predictions, Kriging and similarity, we segment them along strike into these different sectors, which you can see in the very top right plot. So this is the Central American example. Notice that there's all these different colored sectors along the trench boundary here. Within each of those different sectors, there's hundreds of heat flow predictions that we've interpolated using these two different techniques. The trench perpendicular profiles are the two plots on the bottom, one for Kriging, one for similarity. And there's a lot to note about these different profiles, but one thing to note is that similarity on average predicts higher heat flow than Kriging does. So this can be explained by, if you notice the little gold diamonds on the bottom of the bottom plots, those represents the locations of the volcanic vents. Notice that similarity is predicting slightly higher heat flow where those volcanic vents are, because it's bringing in this geologic knowledge, it's seeing high volcanic vents, and therefore I'm predicting high heat flow. But kriging, on the other hand, the little shaded squares that are kind of faded in the background, those are the actual observations. Those are the measurements. Kriging has to fit those measurements. It's like a linear regression. It's trying to minimize the residuals between each of those lines and the data points themselves. So again, there's these subtle differences where similarity is predicting on average higher heat flow than kriging is. But in general, for the case of Central America, we can see that the distributions of all those lines, in other words, the long strike variability seems to be quite small. And you can see the same sort of phenomenon maybe a little bit more clearly in this box and whisker plot on the top, where on the x-axis is all the different sectors, 1, 2, 3, 4, 5, 6, 7, 8 different sectors. The blue boxes represent the distribution of the similarity predictions for each of these sectors. The whitish boxes predict the distribution of heat flow predicted by kriging for each of these sectors. You can see that the blue boxes are on average a little bit higher heat flow. And there is some sort of broad arcing trend where the central sectors seem to have higher heat flow, at least predicted by similarity. And there's sort of an opposite trend where you have low heat flow predicted by kriging in sectors 1 through 5, and then it starts to increase and become closer to parity with the similarity predictions in sectors 7 and 8. So the heat flow profiles that we see perpendicular to the trench and along strike, they're kind of all over the place. We have a whole kaleidoscope of profiles. If you were to look at all the other 12 subduction zone segments, you can see that some of them have very similar kriging and very similar similarity predictions. Some of them are wildly different. Some of them have unique kind of almost wave-like distributions of heat flow along strike, almost as if the heat flow is getting higher at part of the segment and then it's decreasing towards another part of the segment and then increasing again. So we see a lot of variability in these profiles, which then suggests that there is variability in either the lithospheric thickness or perhaps heat transferring processes that are operating in the subsurface, or perhaps the variability can be explained simply by having very low observational density. So the more observations we have, the sort of more precise the predictions get. And so having very sparse data makes the uncertainties quite large, and we can perhaps be getting some apparent features that are not actually real. So the last part here, we are evaluating the distribution of rocks that are sampled from the interface of subduction zones to try to get a sense of what we can find out about the kind of the consistency or the variability of these geodynamic features like coupling depths. What we can gather from the rock record. So rocks are getting sampled at these depths. It's likely that the depths that rocks are getting recovered along the interface represent particular mechanical changes along the interface, which perhaps correlate with things like coupling depths. So first we look at the empirical observations. There's a couple studies that have kind of put together compilations of metamorphic rocks, PT estimates of high pressure metamorphic rocks. Namely, well, in this figure, what I'm plotting is in red, the sort of filled, the shaded red contours are the distribution of PT estimates from the Agard et al. 2018 data set. The green unfilled contours are the distributions of PT estimates from Peniston, Dorland et al. In 2015. And all of the black points on here are the actual PT estimates. So you can see that there's some similarities and there's some differences in terms of how these PT estimates are distributed. GARD and others include a lot more low temperature, high temperature, low pressure rocks that are related to initiation. And Pennis and Dorland et al. Include a lot of ultra high pressure rocks that are really not related to steady state subduction, but they're more related to the onset of continental collision. But regardless, something to point out here is that, from the metamorphic rock record, it seems like the distributions of PT estimates are pretty continuous. In other words, there are no gaps. There are some peaks where we have a lot of samples, but they are distributed, especially with respect to pressure, pretty continuously from low pressure to high pressure. So we ask here, where are rocks recovered along subduction zone interfaces? Are they sampled continuously or at discrete depths? And how does the recovery of these rocks relate to something like coupling depth? And how do recovery rates and distributions vary from subduction zones to subduction zones? In other words, are rocks preferentially recovered from certain settings? And could variations in coupling depth maybe explain the smooth distribution of PT estimates? And lastly, how do numerical and empirical PT distributions compare? Can numerical models reliably indicate PT conditions experienced by rocks? And how do we interpret global compilations of PT estimates, the empirical compilations? So what we do is we trace a bunch of markers in the 64 numerical experiments that that I introduced in part 1. We go back to those experiments. We basically select the entire region of oceanic crust for each of those 64 models, and we look at through time where those markers go in the model domain. And we're trying to figure out which markers are getting recovered, or in other words, which markers are getting detached from the downgoing plate and underplated to the upper plate. And which markers are getting successfully subducted. But the challenge here is that we don't know a priori which markers are going to get recovered or underplated and which markers are going to get subducted. And so what we do is we write what's called an unclassified or an unsupervised classification algorithm to, quote, recognize recovery in these numerical simulations. What the recovered markers represent is markers that they represent rock fragments that get detached and underplated. And so although the majority of these markers don't get exhumed to the surface, they are the corollary or the most direct comparable samples to compare to the empirical data sets. So on the right, here's kind of what it looks like. So on the top plots, on both of the top plots, we're seeing this is a distance, depth, time domain. So this is following the markers as they kind of go down into a subduction zone. So the top left plot is showing all the markers that are getting successfully subducted. So they're just kind of cascading all the way down to the bottom of the model. And the top right plot is showing not the PT paths, but the actual paths, paths in space and in time that the markers take. These are the markers that the algorithm is classifying as recovered. You can see that they begin to fall down into the subduction zone, and then they get detached and they kind of get underplated and they sort of move in sort of interesting ways, but they never get subducted. So this is what the algorithm is classifying as these markers are getting recovered, these markers are getting subducted. On the bottom plots, where it's the pressure, temperature, time domain. So for the markers that are getting subducted, which is the bottom left plot, you'll see that they are increasing in pressure and increasing in temperature, and they are just getting completely subducted. The bottom right plot is showing the PT paths of the recovered markers, and the white mesh that you see there represents the antigrite out reaction in the mantle. So this is where antigrite is dehydrating. It's a temperature sensitive reaction. And remember that in the models, this is directly associated with the point at which the slab and the mantle couple. So none of the markers that are getting recovered are making it beyond the coupling depth. This is intuitively reasonable, and this is also what we see in the numerical data. So here's an example of how we do some calculations to look at how all these recovered markers vary with respect to subduction zone parameters. So our goal is to try to find, we sample out or we select out just the markers that are getting recovered, and we want to compare the distribution of those recovered markers. We want to understand where are they getting recovered from and how the recovery of those markers changes when we change different subduction zone parameters. So what we do is, because we have millions of these markers, we look at just the two most important modes of recovery. So the first mode, what we call mode 1, is the highest peak. It's the highest density, the location in PT space where most markers are getting recovered from. That's what we call mode 1. This is like the statistical mode. Most of the markers are getting recovered from mode 1. On the left plot, you can see mode 1 corresponds to very near the MOHO. So this grayscale is showing the viscosity in a log scale. And mode 1 turns out to be usually kind of right around a gigapascal, very near the continental MOHO. Mode 2 represents the deepest or the warmest peak of markers, high density peak of markers. So after we find the first mode, we ask, okay, this is where most markers are getting recovered from mode 1. Where is there another peak of deeply subducted markers that's also getting recovered? We want to identify that peak, the most deeply subducted markers. This is what we call mode 2. And mode 2 usually corresponds to the coupling depth near the antigrite dehydration reaction. So we go through all 64 models, all these millions of markers. We find the first and second mode for each of these markers, and then we can compare those modes to the subduction zone parameter. So this next plot is there's a lot on here. So I won't walk you through the whole thing, but the notion here is that where markers are getting recovered does vary with respect to the initial conditions for these different models. So the major recovery modes, mode 1 and mode 2, they correlate with certain subduction zone parameters, namely the oceanic plate age, the velocity, and the upper plate thickness. So we see various correlations, some weak, some strong. So for example, the pressure mode 1 and pressure mode 2, we see that the pressure or the depth at which markers get recovered is correlated more strongly with the oceanic plate age and the convergence velocity. But the deepest markers that get recovered, which is represented by pressure mode 2, which is kind of the orangey color box and whisker plots, second to the last on the right. Pressure mode 2 represents the deepest markers that get recovered. That more strongly correlates with convergence velocity and correlates also slightly more weakly with the thickness of the upper plate. Okay, so we have all of these different correlations and non-correlations, but really the story here is that the recovery of markers is dependent on these different initial conditions. The most surprising and probably the most interesting part of this last study, looking at markers, is something that we're calling the marker recovery gap. This is a very surprising result. Basically, if you take a look at the empirical data, which is the red filled contours from the Agard et al. 2018 dataset, the green unfilled contours are the distribution of PT estimates from Peniston Dorland et al. Dataset. So the red contours and the green contours are the empirical data. These are PT estimates from actual rocks and where they are distributed in PT space. The black point cloud and the blue Tanaka contours represent the numerical data. So you gather up all of the recovered markers in all of our 64 simulations, and you look at the distribution at where those markers get recovered in terms of their maximum metamorphic conditions. And we find that by and large, most markers get recovered at around the MOHO at about 1 GPa. Like almost all of the markers, a huge majority of the markers get recovered at the MOHO or near the MOHO. Now, very few markers, the very few markers that go past the MOHO and get recovered at deeper depths, none of those markers seem to get recovered at the same PT space where we have the highest density of natural samples. So you can see that I've drawn some pink arrows here. One is pointing to the marker recovery gap, which is this region in here. So most of the empirical PT data, at least a lot of them, they cluster right around 2-ish gigapascals and about 500, 550 degrees C. In fact, there's like a funny joke among the alpinists that you don't even have to measure the pressure temperature of rocks in alpine blue schists and eclogites, because I already know that they're going to be about 2 gigapascals and 550 degrees C. There's so many rocks that come from that particular condition, but we don't see any markers getting recovered from those conditions in our model. So this gap is curious. We don't really have a great explanation for why this occurs, other than that perhaps the numerical simulations are either missing some recovery mechanism. Some recovery mechanism is just simply not implemented well in the numerical models, and so it's not representing reality that well. Or another explanation that I'm tending to favor is that the empirical data sets, if you take them as a whole, are biased towards certain conditions. So petrologists, what we do is we typically tend to sample and resample rocks, particular rock types that are amenable to thermodynamic calculations. And those rock types get sampled over and over and over again. And if they get sampled over and over and over again, especially from similar localities, they're going to sort of bias, they're going to build this sort of biased picture of the actual distribution of where rocks are getting sampled in subduction zones. And perhaps this is an explanation for why there's a marker recovery gap here. And so with that, I see that I'm pretty much out of time, and I want to leave some time for a couple questions. So I'll just, I will end there. And thank you very, very much for your attention. And if anybody has some questions, I'd be happy to take them.
Thanks so much, Buchanan. Donning, did you have a question? I saw you.
No, I was clapping. I think it's great talk.
Okay. Yeah, if anyone has any questions, feel free to unmute and ask, or put your question in the chat.
I see one comment in the chat here. It should be mentioned that the coupling discussed here is distinct from seismic coupling controlling megathrust earthquakes. Thank you for that distinction. I think that was put at the beginning of the talk.
Yeah, you're welcome. I guess this type of coupling that you're talking about, maybe it could be called geodynamic coupling. It's fully viscous, right?
That's right. It's called many different things, and it's a jargon. It's a jargon thing. So yes, seismologists typically, when they mean coupling, they mean seismic coupling. In other words, this sort of stick slip motion, the part of the subduction interface that can generate megathrust earthquakes. But geodynamicists, when we talk about coupling, we typically are referring to mechanical or viscous coupling. where the viscosity or the strength of the slab and the overlying mantle are becoming close enough that they're exerting a drag force on each other.
Yeah. And you can actually see the focal mechanisms representing interplate earthquakes, small interplate earthquakes, for example, die away maybe around 60 or 70 kilometers depth. You simply don't find interplate consistent focal mechanisms below that depth. So I guess I was wondering, how confident are you that your convection model or geodynamic model has enough physics in it that it's really picking up how deep these samples go? Because there are examples of samples that have been claimed to come from 80 kilometers depth and even 400 kilometers depth in the Alps. And there's plenty of eclogite, I think.
Yes, this is right. This is an ongoing, a kind of an ongoing discussion in the metamorphic petrology community. Although I don't think anybody has got a great interpretation for the metamorphic rock record as a whole. So what's typically done is, because there's so few samples from each of these different regions, few samples is a relative term. But in general, dozens of samples from the Alps, dozens of PT estimates from the Himalaya, dozens of PT estimates from other places. In combination, we have fewer than 400 PT estimates globally. So there is a trade-off between aggregating data sets to increasing the sort of precision or decreasing the uncertainty at which these samples are coming from, or separating the samples into smaller subsets of data from particular regions. What that does is it kind of makes comparisons in more internally consistent if we're only comparing rocks from a particular subduction zone setting, but it's shrinking the sample size down to a dozen samples. And so when you're making sort of global comparisons to like geodynamic models, you're trading off either making more geologically reasonable comparisons or making more statistically certain comparisons.
Yeah, thank you.
You bet. Good question.
Yeah, Buchanan, I've got a question about the recovery.
Sure.
So, in order when you discuss recovery, you seem to be equating underplating and accretion with recovery. But if you underplate some rocks at say 50 kilometers depth and accrete them to the upper plate, they're still at 50 kilometers depth, they're not at the surface. So you need additional mechanisms to actually get them up to the surface. Maybe I'm wrong, but I don't think you actually built that into your model, or built mechanisms for exhumation into your model.
This is a really great question. So thank you. And it's an important distinction between what we're comparing in these studies and how they can be misinterpreted. So recovery in this sense, I'll try to be very clear here. Recovery in our models is the maximum metamorphic condition at which a rock marker gets detached from the downgoing plate and moves in some way to the interface or to the upper plate. In other words, it's the maximum metamorphic condition at which it is no longer getting subducted. So this is what we're calling recovery in this sense. The models themselves really don't generate any sort of self-consistent exhumation mechanism. There is some markers that do start to move up the subduction channel. Taras Gria has written some papers about this circulation within the channel. We know that this may be occurring in real subduction zones. It's an open question, it's an open debate. And so what we didn't want to do is make any sort of statements about exhumation. We only want to compare the maximum metamorphic conditions for the markers to the rock record, because what the rock record represents is, well, the rock record as it's presented in Agard 2018 and Penniston-Dorland 2015 is their best estimate for the maximum metamorphic conditions for those particular samples. So not the prograde path, not the retrograde path, but the actual maximum metamorphic conditions. And that way we're doing our best job to compare apples to apples. So we just are disregarding exhumation, retrograde paths. We just want to look at maximum metamorphic conditions where the rocks are actually being detached. And so recovery in this sense really means detachment. And this is parlance that I follow after Philippe Agard and his group, who make a distinction between recovery as detachment, and it can be sort of misconstrued, the term recovery as detachment and exhumation, but that's not what we mean in this case.
So I mean, just to follow up on that then. So the point you were making about how in the models you're not seeing recovery from 2 gigapascals pressure or something like that, or 2.3 or something. Mm-hmm. What you're saying is that you're not getting detachment and underplating at those depths in your models.
That's right.
Yeah.
Yep. So if there are rocks that are getting detached there, if that is the true metamorphic condition where these rocks are being underplated and then later exhumed, if we are doing a great job at, modeling that through the retrograde overprint in real metamorphic rocks, then this gap is sort of a literal and metaphorical, gap in our understanding of, this could be a problem with the model, certainly, or there's something that we're not understanding about. There's something that we're misinterpreting in the rock record, or we're doing a poor job at implementing whatever this recovery mechanism is in our numerical simulations. Yeah. Can be maybe a combination of both. Who knows?
Thanks.
Yeah.
So we're at 1 o'clock. So Buchanan, if you're able to stick around for a few more minutes, it looks like we have a few more questions.
Yeah, of course. Yeah. Thank you. Thank you everybody for your time. I really appreciate it.
Bounding, feel free to ask your question.
Hi, thanks for the talk. I was wondering about the plate thickness, which follow-up question from a previous question during the talk. Is it the same? I think this defined by temperatures, but would it be comparable to the like seismic defined LAB, like lithosphere, asthenosphere boundary? Like if you do something like that, can you sort of measure this plate thickness globally using seismic data?
Yeah, great suggestion. This was my first attempt at this problem, but there's a lot of different ways that we could approach this problem. And in the past, people have looked at everything from mantle xenoliths, the pressure estimates from rocks that were extracted from the base of the lithosphere, as far as we know, to heat flow modeling, to seismic imaging. So in an ideal case, in a perfect world, we would have great seismic data co-located with great resolution of heat flow data, and maybe a few petrologic samples of mantle xenoliths that we could all compare to get a really confident estimate for the thickness of the lithospheric plate. And now I'm not familiar with the seismic data and how it's distributed, but it could be more well distributed than the surface heat flow data. The surface heat flow data are pretty sparse, and they're difficult because they're clustered. They're like clustered and they're far apart from each other. And so getting a sense of the 2D distribution is a challenging interpolation problem. And there are, of course, better approaches, or those approaches can be refined from kind of what we've done in this work. But incorporating seismic data is a great idea, and this is something that should be done and would be a great avenue to look at this, no doubt.
Cool. Thanks.
You bet.
Vinha?
Thank you. Great talk. Thank you. Just a clarification question. Is the depth to the oceanic plate under the arc, that depth, is that different from the coupling depths you mentioned? They are conceptually different, right?
They are distinct in a sense.
Mm-hmm.
So the what we understand about about the thermal structure of a subduction zone suggests that they should correspond to each other very closely.
Oh, okay.
So when coupling happens, that is the point at which you start to churn over the mantle wedge.
Mm.
And so you're bringing warm mantle material up into the kind of nose of the wedge. And this should correspond closely to the region where flux melting is occurring to produce volcanic arcs.
Mm-hmm.
However, they are distinct. The measurement, measuring or estimating coupling depth is different from measuring or estimating this D value, which they use. People use have used the hypocenters of earthquakes at the top of the slab, and you just project a line straight beneath. You know the location of the arcs because that's on the surface. So you just go to that location. You look at the earthquake catalog. You project a line straight down. And you use the hypocenters to try to pinpoint the position on the slab. That's D. Coupling is going to be, we know coupling is going to be slightly at a shallower depth, because coupling must be occurring before you're generating arc magmas, because otherwise you're not churning over the mantle wedge yet, and it should be pulled. We call this like the cold nose of the mantle wedge.
Mm-hmm.
So coupling should be up above D a little bit, but it should be probably, I don't know if anybody has any good estimates on this, but I would guess it should be within, I don't know, definitely within tens of kilometers, and maybe, within a few kilometers of D. But again, the uncertainties of both of those things, the coupling depth and D, the best estimates that we could have for them, they would both almost be identical points within uncertainty anyway. So I don't even know if we have great enough methods, precise enough methods to distinguish those measurements actually.
Yeah. Thanks.
I hope that clarified that.
Very quick follow-up.
Please.
Guessing the formation of this arc, the melting, is not only dependent on temperature but also on pressure, right? And is pressure also taken into consideration in studying the relation between this D and the coupling depth?
Another good question. I'm not sure exactly how to answer it, other than both of these measurements are sort of geometric measurements of subduction zones, and I don't know. In terms of measuring D, the procedures is pretty simple, and it relies mostly on hypocenters of earthquake. So I don't think there's much of a pressure correction there, although there's certainly a bunch of uncertainty on what's causing these earthquakes at those depths. With respect to coupling depth, the estimate involves understanding something about the rheology of the rocks that are in the interface. And that certainly is a pressure dependent process. So in our models, the coupling is induced. Basically, it's kind of the location of coupling is controlled, so to speak, by the location of this particular dehydration reaction that involves serpentine. although the reaction itself is it's much more temperature dependent than it is pressure dependent, the uncertainty on where that reaction is located in terms of pressure would certainly wiggle the estimate that we would get for coupling depth up and down a bit. So
Yeah, I got it.
yeah, I hope that is along the lines of your question.
Yeah, I got what you mean. Thank you very much.
Mhm.
Great talk.
Thanks.
Okay, it looks like we don't have any other questions. But thank you so much, Buchanan. This was a really interesting talk, and I think kind of puts into perspective, what we're sampling and why it's there. So.
Great. I'm glad I made some inroads there. Got some ideas turning. So thank you very much for everybody's time, and thanks for the invite. It's been a lot of fun.
Thank you so
Good luck
much.
with everything at Miami.
Thank you.
Have a good one.
Bye.